Let's rewind to the 1970s. The trucking industry was at a crossroads. Emissions regulations were tightening, fuel prices were climbing, and drivers needed more power than ever before. The industry was desperate for an engine that could meet the new Clean Air Act regulations while still delivering the raw power that truckers demanded for hauling heavy loads across America's highways. Enter Cummins with their answer, the 855 Big Cam. This wasn't just another diesel engine. This was 14 liters of American engineering packed into an inline-6 configuration. The numbers alone tell a story of absolute dominance. 855 cubic inches of displacement, bore and stroke measuring 5.5 by 6 inches, and a camshaft so massive it gave the engine its legendary name. The compression ratio varied depending on the specific variant, ranging approximately from 14.1 to 1 up to 15.5 to 1. This high compression was crucial for extracting maximum energy from every drop of diesel fuel. The engine could rev up to 2,100 RPM for peak output, though most of its legendary torque came at much lower engine speeds, exactly where truckers needed it most. But here's what made truckers fall in love with this beast: the torque. We're talking anywhere from 1,000 to 1,650 pound-feet of torque. Whether you were hauling timber up mountain passes, pulling farm equipment through muddy fields, or moving freight across the endless plains, the Big Cam delivered power that felt limitless. The Big Cam's secret weapon was right there in its name. Cummins designed one of the largest camshaft diameters of its era, completely reimagining how the valve and injection systems worked together. This wasn't just an incremental improvement over previous designs, it was a fundamental reimagining of how a diesel engine could operate. The massive camshaft allowed for completely redesigned valve timing and a revolutionary injection system that gave engineers unprecedented control over fuel delivery and combustion timing. This innovation allowed for precision fuel delivery and timing that was years ahead of its competition. And the result? An engine that could produce anywhere from 250 horsepower up to 475 horsepower depending on the configuration, with industrial variants pushing 450 horses. And remember, this was in an era when many competing engines struggled to break 300 horsepower reliably. The technical innovations were groundbreaking for the 1970s. Cummins implemented what they called demand flow cooling, a system that only cooled the engine when necessary. Think about what a brilliant concept this was. Traditional cooling systems constantly circulated coolant through the engine, whether it needed cooling or not. This constant circulation required power. Power that was being stolen from the drivetrain, power that could have been moving the truck forward instead of running a water pump unnecessarily. The demand flow cooling system changed all that. It monitored engine temperature and only activated cooling when truly needed. This brilliant design improved efficiency dramatically, freeing up more horsepower for actual work instead of wasting it on constant cooling. In practical terms, this meant more power available at the wheels, better fuel economy, and less parasitic loss. With an oil capacity of around 44 quarts, that's 11 gallons of oil. This engine was clearly built for the long haul, with lubrication capacity that ensured every moving part stayed protected, even under the most extreme operating conditions. Reports of Big Cams running 700,000 miles before needing an overhaul weren't just marketing hype. These were real-world numbers from real truckers putting in real miles. These were engines that saw daily abuse, loaded to maximum capacity, running through desert heat and Arctic cold, idling for hours at truck stops, climbing mountain passes day after day, and they just kept running. The fuel efficiency was remarkable for its time too. Despite its massive size and power output, the Big Cam's innovative timing system actually improved fuel economy compared to earlier 855 models and competing engines. This seems counterintuitive, doesn't it? How does a bigger, more powerful engine use less fuel? The answer lay in that revolutionary camshaft design and injection timing system. By optimizing when and how fuel entered the combustion chamber, Cummins engineers extracted more energy from every drop of diesel. In an era when fuel costs were skyrocketing and eating into truckers' already thin profit margins, this efficiency advantage made the Big Cam not just desirable, but economically essential for many operators. The engine paid for itself in fuel savings over its operational lifetime. The Big Cam also held another important distinction. It was Cummins' first engine to meet the Clean Air Act regulations and noise standards of the 1970s. This was no small feat. Environmental regulations were new and strict, and many manufacturers struggled to meet them without sacrificing power and reliability. Cummins managed to do both, meet the regulations and deliver more power than ever before. This compliance was a major selling point and gave the big cam a competitive advantage in a market where some competitors were still scrambling to meet basic emission standards. The noise standards compliance was equally impressive. Anyone who's been around old diesel engines knows they can be deafeningly loud. The big cam, while certainly not quiet by modern standards, was engineered to operate within acceptable noise limits for the era. This meant drivers could operate these trucks without the hearing damage that plagued earlier generations of truckers, and trucks could access areas with noise restrictions that prohibited older, louder engines. But if the Cummins 855 big cam was so incredibly powerful, so reliable, and so beloved by everyone who operated one, if it could run for 750,000 miles and still keep going, if it met the Clean Air Act regulations when they first came out, and if truckers literally chose their rigs based on whether they had this engine under the hood, then why on earth would anyone want to ban it? What could possibly make an engine that was this good become unwelcome on modern roads? What fatal flaw lurked beneath all that legendary performance? Well, the very things that made the big cam legendary in the 70s and early 80s became its death note as the world changed around it. The engine wasn't banned because it was bad. It was phased out because the world moved forward, and this mechanical masterpiece couldn't keep up with the pace of change. You see, the big cam operated on a mechanical fuel injection system with injection pressures around 2,200 psi. For its time, this was cutting-edge technology. It represented the pinnacle of mechanical fuel injection engineering. But here's the thing about mechanical systems. They have inherent limitations. No matter how precisely machined, no matter how carefully calibrated, there's only so much you can do with springs, cams, pushrods, and mechanical linkages. As emission standards grew stricter through the 80s and into the 90s, mechanical systems hit their ceiling. Think about what fuel injection needs to do. It must deliver precisely the right amount of fuel at precisely the right moment in the combustion cycle at precisely the right pressure. And it needs to do this while accounting for engine temperature, load, altitude, ambient air temperature, throttle position, and dozens of other variables. A mechanical system can handle some of this, but it can't handle all of it with the precision that modern emissions standards demand. There's only so much you can fine-tune fuel delivery when everything's controlled by springs, cams, and mechanical linkages. Electronic fuel injection systems, which were emerging in the 80s, could adjust injection timing and fuel quantity hundreds of times per second based on real-time sensor data. The big cam's mechanical system, brilliant as it was, simply couldn't compete with that level of precision and adaptability. Now, every legend has its flaws, and the big cam was no exception. Let's talk about what became known among truckers as the Minnesota problem, though it affected drivers anywhere temperatures dropped below freezing. Diesel fuel thickens in cold weather, becoming gel-like at extreme temperatures. The mechanical injection system couldn't generate enough pressure to properly atomize this thick, cold fuel. Without proper atomization, you can't get combustion. Without combustion, you're going nowhere. Drivers had to rely on glow plugs or ether sprays just to coax the engine to life in cold weather. Glow plugs would heat the combustion chamber, giving the fuel a fighting chance to ignite. Ether, sprayed into the air intake, was so volatile it would ignite even in cold conditions, helping to get the combustion process started. But both solutions were band-aids on a fundamental problem. This was a serious operational challenge that cost drivers time and money. In the modern logistics world where every minute counts, where just-in-time delivery schedules leave zero margin for error, this quirk became increasingly unacceptable. A driver who couldn't guarantee their rig would start in cold weather was a driver who couldn't guarantee they'd make their delivery window. And a driver who couldn't make delivery windows was a driver who wouldn't stay employed for long. But the cold start issues were just the beginning of the big cam's challenges as the industry evolved. The mechanical complexity that gave it such character also made it harder to optimize for changing regulations. You have to understand that emissions regulations didn't just appear once and stay static. They evolved constantly, becoming stricter almost every year. While the big cam was Cummins' first engine to meet Clean Air Act regulations in the 1970s, those regulations didn't stop evolving. They got stricter and stricter. What was compliant in 1976 was non-compliant by 1981. What was acceptable in 1981 was illegal by 1986. The regulatory goalposts kept moving, and the big cam's mechanical design couldn't keep up. But how could an engine that was specifically designed to meet government emissions regulations, an engine that was literally praised for being the first to comply with Clean Air Act standards and noise requirements, how could that same engine end up being pushed out of the market because it couldn't meet emission standards? Wasn't it built for exactly that purpose? What changed between the big cam being a compliance champion and becoming an environmental liability? How does an engine go from hero to zero in the emissions game? The answer lies in the relentless march of technology and regulation. When the big cam launched in the mid-70s, it was ahead of its time. It met the emissions standards of that era brilliantly. The engine was a testament to what mechanical engineering could achieve when pushed to its limits. Cummins engineers had squeezed every bit of performance and compliance out of that mechanical injection system. But here's the thing about regulations. They never stop tightening. Throughout the 80s, the Environmental Protection Agency kept raising the bar. Each year brought new requirements for lower nitrogen oxide emissions, reduced particulate matter, and better fuel economy standards. The EPA wasn't being arbitrary. Scientific understanding of air pollution and its health effects was growing, and the data showed that even the clean engines of the 70s were still contributing to serious environmental and health problems. And this is where the mechanical nature of the big cam became its fatal flaw. Electronic fuel injection was emerging, offering precise control over injection timing, fuel pressure, and combustion that mechanical systems simply couldn't match. These early electronic systems were crude by today's standards, but they offered something revolutionary: the ability to adjust engine parameters in real time based on actual operating conditions. These electronic systems could adjust hundreds of times per second, optimizing performance for emissions, power, and efficiency simultaneously. They could sense when the engine was cold and adjust injection timing accordingly. They could detect high altitude and compensate for thinner air. They could monitor exhaust gas composition and make corrections on the fly. The big cam's mechanical injection, no matter how well designed, was fighting with one hand tied behind its back. Let's talk about something else that plagued the big cam as the industry evolved: its sheer size and weight. This engine was built like a tank because it needed to be. That 14-liter displacement, that massive camshaft, that robust construction that allowed it to run for 700,000 miles, all of that came at a cost. And in trucking, every cost eventually gets calculated, quantified, and optimized away if possible. The big cam was heavy. Really heavy. The engine block alone weighed hundreds of pounds more than newer, more compact designs. In an industry that increasingly valued efficiency and payload capacity, every pound of engine weight was a pound less cargo you could legally haul. And in trucking, where profit margins are razor thin and every pound of payload means revenue, this weight penalty became a serious competitive disadvantage. Think about the math. If your engine weighs 500 pounds more than a competitor's engine, that's 500 pounds less product you can haul per trip. Over thousands of trips, that adds up to significant lost revenue. Newer engines were being designed with lightweight materials, aluminum components instead of cast iron, advanced alloys, and clever engineering that maintained strength while reducing mass. These engines could deliver comparable power at a fraction of the weight. The demand flow cooling system, while innovative, also presented challenges as the engine aged and as operators demanded ever higher reliability. In theory, it was brilliant. Only cool the engine when needed, save energy, improve efficiency. It was exactly the kind of clever engineering that made the big cam special. In practice, though, it required careful maintenance. The system relied on valves, thermostats, and sensors that needed to be in perfect working order. If operators didn't stay on top of cooling system service, if they skipped maintenance intervals, if they used the wrong coolant, or let the system get contaminated, the inconsistent cooling could lead to engine stress and premature wear. And let's be honest about truck maintenance in the real world. Not every operator was meticulous about servicing their equipment. Some drivers and fleet managers would push maintenance intervals, skip inspections, or use cheaper fluids that didn't meet specifications. With a traditional cooling system, you might get away with this neglect for a while. With the demand flow system, the consequences were more immediate and more severe. Hotspots could develop in the engine, gaskets could fail, head warping could occur, and suddenly that legendary reliability started looking less reliable. Now, here's the twist in this story that nobody saw coming. The Cummins 855. Big Cam wasn't killed by competitors. It wasn't killed by government regulations. It wasn't even killed by changing market demands or technological obsolescence, at least not directly. The Big Cam was killed by Cummins itself, specifically by the success of its own engineering team. And this is perhaps the most bittersweet part of the entire story. You see, the engineers at Cummins who created the Big Cam didn't rest on their laurels. They kept innovating, kept pushing boundaries, kept asking themselves how they could build something even better. And in doing so, they created something that would make their masterpiece obsolete: the N14 engine. The N14 represented everything Cummins had learned from the Big Cam, but executed with next-generation technology. It used electronic controls, the CELECT system, which gave it unprecedented precision in fuel delivery. It offered better emissions compliance, because those electronic controls could optimize combustion in ways the mechanical Big Cam never could. It improved fuel economy further, because it could adjust to operating conditions in real time, and critically, it could be easily adapted to meet future regulations through software updates, rather than requiring wholesale mechanical redesigns. And Cummins, to their credit, made a hard decision. They could have kept producing the Big Cam alongside newer engines, letting it fade slowly into obscurity while customers gradually transitioned to newer models. This would have been the safe, comfortable approach. Maintain two product lines, let the market slowly decide, avoid forcing anyone to change before they were ready. Instead, they made the call to phase out the Big Cam decisively in the mid-80s, pushing their customers toward the future, whether they wanted to go there or not. This took courage. The Big Cam was still selling well. Customers loved it. It was profitable. But Cummins' leadership could see the writing on the wall. The future belonged to electronic engine management, and the sooner they fully committed to that future, the better positioned they'd be as a company. This created a strange situation. Truckers who loved their Big Cams suddenly couldn't buy new ones. If you wanted a new Cummins engine, you were getting an N14 whether you liked it or not. The parts supply began to shift toward newer models as Cummins focused manufacturing resources on current products. Dealers started training their mechanics on the new electronic systems instead of the mechanical Big Cam. Independent repair shops had to decide whether to invest in the diagnostic equipment needed for newer engines or stick with the aging Big Cam fleet. Insurance companies and fleet managers started pressuring drivers to upgrade. Insurance rates began creeping up for older equipment. Fleet managers looked at the total cost of ownership and saw that newer engines, despite higher purchase prices, penciled out better over the long run due to improved fuel economy and reduced maintenance costs. It wasn't an official ban, but it might as well have been. The economic and regulatory pressure was pushing the Big Cam toward extinction. Some jurisdictions even began implementing power and emissions restrictions that effectively prohibited older engines, like the Big Cam, from certain routes or applications. California, always at the forefront of emissions regulations, started requiring newer engines for trucks operating in certain areas. Some cities implemented restrictions on older diesel engines in downtown areas during high smog days. The engine that had too much power was being told it wasn't clean enough, efficient enough, or modern enough for the new era of trucking. The discontinuation of the Big Cam in the mid-80s marked the end of an era. It wasn't just the end of an engine model, it was the end of a philosophy of engine design. The Big Cam represented the absolute pinnacle of what could be achieved with purely mechanical engineering. Everything after it would rely on computers and electronics to some degree. The last Big Cams rolled off the assembly line, destined for a working life that, ironically, would last decades longer than Cummins was producing them. Some of these final engines are still working today, 40 years later, still hauling loads, still earning their keep. They've outlived entire fleets of newer engines that replaced them. But here's what makes this story fascinating. The ban of the Big Cam wasn't really about the engine being too powerful. That was never the problem. Power was the whole point. That massive torque output was the feature, not a bug. The real issue was that the industry had moved to a new paradigm, one where electronic control, emissions compliance, and fuel efficiency trumped raw mechanical power and simplicity. The Big Cam's massive torque output, its legendary reliability, its roadside repairability, None of these advantages could overcome the fundamental shift toward computerized engine management. In trucking, agriculture, and industrial applications, the market demanded engines that could meet increasingly strict environmental regulations while maintaining profitability. The big cam could meet the profitability requirement. Those low fuel costs and minimal maintenance made it economically attractive. But it couldn't meet the emissions requirements, and that was non-negotiable. Fleet operators did the math, and the math was brutal. Newer engines might cost more upfront, but they saved money on fuel over their operational lifetime. They faced fewer regulatory hurdles, no restrictions on where they could operate, no special permits required, no risk of being caught on the wrong side of emissions regulations. And they could operate in any climate without the cold start drama that plagued big cams in winter. The big cam's mechanical simplicity, once its greatest selling point, became a liability in a world that valued adaptability and compliance above all else. A mechanical engine was what it was. You couldn't just reprogram it to meet new regulations. An electronic engine could be updated with new software, its behavior modified to meet changing requirements without touching the hardware. Today, the Cummins 855 Big Cam occupies a special place in diesel history. It's mentioned with reverence in trucking forums and diesel enthusiast groups. Restoration specialists command premium prices for their services rebuilding these engines. Vintage trucks with big cams command premium prices at auctions, not despite their age, but because of it. Collectors seek them out specifically, willing to pay far more for a truck with an original big cam than for otherwise identical trucks with newer engines. So, would you choose the big cam's raw power and simplicity, or an engine with modern efficiency? Drop your answer below, and if this story fired you up, hit that subscribe button.